Hey guys, this is the center console bezel from 2006 Nissan's Navara. It's a thin cup-shaped shell with lots of plastic clips and mounting holes, which make it pretty tricky to 3D scan both sides and get them aligned properly. So this is a pretty challenging 3D scan example. I'll be testing it with 4 Creality laser scanners to see how each one performs, looking at tracking, scanning speed, and then comparing the result side by side. I will start with the Creality Sermoon X1, which is the most expensive scanner in their lineup. After that, I'll test the Sermoon S1, the Sermoon P1, and finally the classic Raptor Pro. I'll be using the scan results for reverse engineering in CAD, which I will walk through in my next video, so stay tuned for that. My Creality K2 Plus has a 35 by 35 cm build plate. That's about 2 cm too small if I print the part flat like this. But if I stand it upright, it ends up 2 cm too tall and needs way too much support. I might have to split the model and join it mechanically instead. Let's take a moment to talk about how to get a complete scan of this bezel. This bezel has a cup-like shape. When you place it on the table with the convex side facing up, it's easy to capture all the surfaces since the walls don't block the scanner from picking up the markers. And that way, you can easily capture a clean, perfectly defined sidewall. But when you flip the bezel to scan the other side, the concave side faces upward. As you scan along the walls themselves block the scanner from seeing the markers placed inside. This leads to poor quality when scanning the sidewalls with the concave side facing upward, and you will have to manually clean them up after alignment. That's why I won't be scanning any of the sidewalls in that orientation. So without overlapping sidewalls, how do you align the two scans? You can do it by using global marker scanning, relying on the markers attached to the sidewalls for alignment instead. There are 2 sizes of refractive markers, 6mm and 3mm. The 6mm ones are definitely the best for tracking since the scanner can pick them up from a longer distance. Start by placing the 6mm markers directly on the object, but avoid sharp curves and don't put them too close to the edge. Leave about 1 or 2 mm of spacing from the extreme edge. Markers should also be placed across different planes since you will need to shift the scanning angle to capture all the surfaces. Since this area sits close to the table, I don't need to stick marker sticker directly on it. I can just place a few markers cube instead. This area is too narrow for 6mm markers, so I'll use the 3mm ones instead. You might wonder why I'm not using external markers like I have done in many of my other videos. The bezel is simply too wide and too tall, and I also need to shift the scanning angles to fully capture the surface. In this case, external markers just won't work. Right now, I'm testing the scan without using spray. The Creality laser scanner can capture black objects, but like any scanner, it slows down when the surface is both black and reflective. Personally, I prefer using spray and scanning with a lower frame count. I have now applied a thin coat of SKD-S2, a developer spray. It lays down a denser powder compared to AE-SAP, and the smell is noticeably milder. Starting off with the Creality Sermoon X1. Now I'm starting the capture in global marker scanning mode. In this mode, only the markers are registered. That makes the point cloud capture smoother and reduces drifting error compared to scanning without global markers. Next, I will capture the point cloud using a 0.25mm resolution. For the entire scan, I will stick to either cross-line or single-line laser mode. Both give a larger capture area, and with the number of the markers I have placed here, the 7-line mode would struggle to maintain tracking. Now I'm moving on to the back side, starting again with global marker scanning. When you are scanning in this mode, you mustn't miss a marker. If a marker isn't detected during point cloud capture, it might burn out in the data and show up as an open hole in your scan. As I mentioned earlier, this backside has a concave surface pointing upward, so I will avoid capturing the sidewall. If it does get captured accidentally, I'll need to remove it later during post-processing. This is Creality Scan version 4.2.2. They have moved the plane clipping button down to the bottom menu. It used to be in the upper menu, and it took me a while to find it. Now you can select 3 points to create the clipping plane. Previously you could only select 3 markers. I'll use the single body selection tool to invert the selection and delete the unwanted data with just 2 mouse clicks. Next, I will select both scans and run point cloud fusion. I will set the resolution to 0.25mm, which was the intended resolution when I captured the scans. You need to fuse the scan data to get the final result. Some viewers ask me why their scans look poor. In fact, it's because they didn't run the fusion step. Next, I will align the 2 scan datasets. I click on the alignment tool, choose marker alignment, and then switch to manual mode. I will rotate both scans to the same orientation and pair 3 markers for alignment. Notice that the scan in the right window has no sidewalk captured. That's why I'm using marker alignment instead of feature alignment, which requires overlapping point clouds. I pick 3 pairs of markers around different corners, then click Preview and Apply. Now the 2 scan datasets are aligned, but they are still separate. To truly join them together, you will need to run the meshing function. There is a triangle count display in the upper left corner. Use that number as a reference when setting the triangle count during meshing. After meshing, you can export your data either as a point cloud in ASC format or as a mesh in STL or OBJ format. Let's move on to the next scanner, the classic Creality Raptor Pro. The Raptor Pro was launched in February 2025, about 4 months after the Raptor X, so it's not the latest laser scanner. Still, quite a number of my customers are using it because it produces truly usable results for precision reverse engineering. The point cloud quality is on par with the newer Sermoon series. The main differences between the Sermoon series and the Raptor Pro are the scanning speed and the absence of a single line laser mode. This object has a thin bezel and only a small surface area for attaching markers. For parts like this, the minimum requirement is a scanner with cross-line lasers. If you try scanning this in a 7-line laser mode, it definitely won't be able to track with such a limited number of markers. For the scanning experience with this console bezel, the Raptor Pro runs much slower than its counterpart, about half the speed of the X1, even though it lacks a single-line laser mode. It doesn't use wide-angle lenses, which actually makes it capable of scanning deeper than the Sermoon series in cross-line mode. I also noticed that the tracking isn't as smooth as with the Sermoon X1. Its capture range is smaller, so it doesn't see the markers as widely as the X1. Now let's move on to the next scanner, the Creality Sermoon S1. The Sermoon S1 was launched in August 2025. It was Creality's first scanner to use wide-angle lenses equipped with high-speed image processor, and for the first time in this price range, we saw a truly usable single-line laser mode. The scanning speed and tracking performance are very similar to the X1. The difference is that the X1 delivers much higher accuracy. Its real-world error is only about 10 micron, while the S1 comes in at around 40 to 50 micron. The X1 also uses wider angle lenses than the S1, but in practical scanning, the tracking performance feels the same. Now let's move on to the last scanner in this lineup, the Creality Sermoon P1. With the latest firmware update, the P1 automatically casts the screen from your PC once the Wi-Fi connection is established. The P1 was launched in February 2026, making it Creality's latest 3D scanner. Its scanning speed is a bit slower than the S1 and X1, but still noticeably faster than the Raptor Pro. The P1 also uses wide-angle lenses, though not as wide as the S1, so its tracking performance sits somewhere between the S1 and the Raptor Pro. Now I'm connecting the P1 to my PC in Wi-Fi mode. The scanning speed reaches 80 frames per second, which is considered very fast. It feels almost like using a cable connection, making it very convenient when scanning parts like this where you need to orbit around the object. The previous scanners in this video were connected with 4 meters USB cables, which felt clunky and constantly got stuck on my table whenever I walk around it. On top of that, I had to keep turning my head toward the monitor. With the P1, I can look directly at its built-in screen during the scan, which makes the whole process far more convenient. Even though the P1 uses the same 22 cross-line laser as the Raptor Pro, it's built with a different projector module and camera, which gives it better tracking performance. When scanning this console bezel, it doesn't feel any different compared to the S1. Let's take a look at the scanning results side by side. Each scan contains a polygon mesh of 10 million faces. Opening all 4 at once in this render scene consumes the full 24 GB of my VRAM. Looking at the X1, it produces a sharp and clean scan. All 4 scanners were able to align the front and back scan data successfully without any error. Moving on to the S1, it produces a result very similar to the X1. Moving on to the P1, its final result is also very similar to what we see from the X1 and S1. And here comes the Raptor Pro. It produces the same level of point cloud quality as the Sermoon series. Looking at the back side, here is the X1. All the clips and mounting holes are captured. The S1 also gives the similar result. And here is the P1. And finally the Raptor Pro. All 4 scanners produce similar results, each fully usable for precision reverse engineering, which I will demonstrate in the next video. The X1 should deliver the most accurate output, but since this part is plastic, it doesn't require 10 microns of accuracy. Any of these scans will do the job. Alright, thanks you guys for watching. I'll see you in the next video.